Welcome to the second part of the webinar on the EICASLAB demo real-time embedded for BeagleBone Blackboard. It is the continuation of the first introductive part. We will focus on the first control design phase, the modeling and like real-time simulation. The modeling and like real-time simulation mode allows to design the control algorithm and to test it in a simulated environment through like real-time simulations in interaction with a simulated rotating table. So, the main modeling and like real-time simulation mode purposes are to model the plant, to run and validate the model, to design the control algorithm, and to run and validate the algorithm against the simulated plant. We present in this slide a part of the project used for the control design development. It is the main graphical layout of the project, called System Layout, developed using the EICASLAB Sim Builder tool, which is a tool dedicated to the plant modeling and control design activities, providing a pre-organized environment composed by a set of graphical layouts organized in a hierarchical way, referring to the plant control and mission task. The plant model is implemented in the rotating table block, the control algorithm in the processor block. Then, 3 mission blocks are used in order to provide external disturbances to the plant, to provide the desired trajectory, and to compute the actual performance. Finally, there are 2 converters for interfacing the analogical plant to the digital control. In modeling and like real-time simulation, all the activities of the project, and specifically the plant simulation and control strategy, run simulated in the EICASLAB RCP platform. Once the project is configured, you can carry out the simulations through the Sim tool that provides a professional simulation of your control system through a like real-time technique capable to accurately emulate the execution of the control architecture running in the final target. It provides diagrams, editing of runtime parameters, and recording of data in POST files that can be offline analyzed through the POST tool. Let's now show a practical demonstration working directly with the EICASLAB software suite. We begin working in modeling and like real-time simulation, but since for the next operative modes we will need to access the real-time capabilities, we run EICASLAB as superuser. In fact, the EICASLAB installer automatically creates 2 links on the user desktop. One for running EICASLAB as normal user, which works for all the tasks except the real-time ones, and one for running EICASLAB as superuser. So let's run EICASLAB as superuser. You have to provide the superuser password. Once you have launched the EICASLAB demo, the first EICASLAB window gets open. It is the master tool window from which you can manage all the EICASLAB tools. In the master tool window, select the demo menu. You can see the 3 projects included in the demo. The RG control project, that includes a control algorithm automatically generated by the EICASLAB Automatic Algorithm Generation Advanced feature. Then, the user control project, that has the same structure as the RG control project, except that the control algorithm is not implemented, letting the user free to implement his own control strategy. Then, the plant project, which is a real-time emulator of the rotating table, which substitutes the real rotating table interacting with the real-time control application. It is specifically created for this demo for avoiding the use of the real plant. Now let's open the RG control project. The Sim Builder tool gets open, showing the graphical system layout of the demo project. The project is in modeling and like real-time simulation, as you can check by viewing the operative mode toolbar. We have already described the blocks of the system layout. We now briefly consider their connections. The rotating table block receives 2 inputs, a command coming from the control, converted by a digital to analogical converter, and a disturbing torque coming from the disturbance mission block, and provides two outputs, the angular position of the motor and the angular position of the rotating table. The processor block receives as input the angular position of the motor converted by an analogical to digital converter and the desired angular position provided by the trajectory generator mission block. As output, the processor provides the command for the rotating table. You can open any block for viewing and, in general, modifying its structure by double-clicking on it. Let's open the rotating table block. It is a block graphically programmed through the blocks of the continuous plant library. We don't consider here the details of the model. Just note that the upper part of the scheme models the electric motor that receives a commanded current. The central part models the transmission torque transmitted through the mechanical jar whose elastic deformation and hysteresis are considered. And the bottom part models the load that is the rotating table. Each block of the graphical library has a set of parameters whose meaning is explained in the full EICASLab user manual. It's possible to open the parameter window for viewing their values. Opening the processor block, you see the processor layout containing 4 blocks. The control block, where the control algorithm is implemented, which is the application software, target independent. 2 blocks representing the inputs of the processor, and 1 output block. As already said, the control algorithm is implemented by the Automatic Algorithm Generation Advanced feature, oriented to automatically design and generate the complete control algorithm and related software. You can view the structure of the control, selecting the ARG structure item and clicking on the Show Scheme button. It is based on a model-based approach that includes the design of a reference generator, a state and disturbance observer, and a closed-loop control. In fact, this block is already programmed in this demo, but in general, you have to provide a linear model of the plant through the AAG model window and to provide the dynamics of the control through the AAG poles windows. Let's now consider the scheduling parameters of the blocks. Select the scheduling menu of the SimBuilder tool and open the Activities Scheduling window, containing the scheduling parameters of all the blocks. All the parameters are given as a multiple of the simulation step. Consider first the phase, which is the time at which the block has to be called for the first time. Then there is a period and the duration, that is, the execution time considered the worst case. The duration is emulated considering, for any block, 2 periodic functions. An execution function dedicated to update the block state, and an output function dedicated to provide the output of the block only after the stated fixed duration. This approach allows to perform the like real-time simulation, avoiding wrong time zero simulations. When the project is implemented, you can compile it. Click on the Compile button. You can see the report of the compiling process. Then, you can run a simulation. Click on the Run Sim button. Then, the Sim tool gets open. It includes 6 time diagrams, and each one can plot up to 4 variables. So you can monitor during the simulation the behavior of 24 variables. The Sim control panel provides a full control of the simulation through 4 control buttons: the Start, the Pause, 1 step, and the Stop button, while in the right corner you have button for viewing the standard output, the standard error, together with a warning and error counter. Now press the Start button for beginning the simulation. The time diagrams of preselected variables of interest are shown. The commands, the desired and measured position, the control error, the disturbance torque, the elastic deformation, and the transmitted torque. Note that the transmitted torque is not a time diagram, because it provides the transmitted torque as a function of the torsional deformation of the mechanical gear. In the toolbar, there is a menu specifically created for the demo. Select the configuration item. You can select the type of trajectory you want. As we already described, you can choose between a point-to-point mode or a tracking mode. Then select the performance item. Then you can view the performance of the control. EM is the mean value of the rotating table angular position error. ET is its mean square value. ELF is the mean squared value of a low frequency component of the error, obtained by a second-order low-pass band filter with frequency bandwidth of 4 Hz. And EHF is the mean squared value of a high-frequency component of the error. For more technical details about the control of the rotating table, you can refer to the document Rotating Table Test Cases of the EICASLab demo in the EICASLab website. During the simulation, the sim tool can record any variable in post files that can be offline analyzed through the post tool. So let's close the sim tool and in the master tool window open the post tool. In this demo, 4 post files are recorded, containing each one the variables of interest of one block of the project. You can select any variable you want and assign it to a plotting area. Then, clicking on the Start Plot button, the plotting window gets open representing the desired graphs. A predefined configuration is available. Click on the Load Configuration button for selecting the performance.save element already prepared for this demo. Then press the Load button. When the configuration is loaded, you can press on the Start Plot button in order to open the plotting window where all the graphs are configured according to the selected configuration.